All right, well, we're in chapter 4 or chapter 5, section 4, and we're going to be looking at identifying stereogenic centers. In order to identify a stereogenic center, we need to identify a tetrahedral carbon, in other words, an sp3 hybridized carbon, and determine if it has 4 different groups. Now, not necessarily 4 different atoms, but 4 different groups attached. Here is an example. This has 4 different groups attached. The 4 groups that are attached are going to be hydrogen, bromine, there's an ethyl, and a propyl that are attached to this carbon. So things that cannot be a stereogenic center, it would include things that are not sp3 hybridized. So in other words, things that are sp or sp2 hybridized. Only tetrahedral or sp3 hybridized carbons can be stereogenic centers. So if there's only if there's only 2 or 3 domains, that won't count. You have to have 4 domains. It has to be tetrahedral, it has to be sp3 hybridized. All of those, of course, mean the same thing. We'll also find that atoms that have 2 of the same groups attached. So for example, this carbon couldn't be a stereogenic center because it has 2 hydrogens. The hydrogens are identical. You have to have 4 different things attached. This, of course, the methyl group here has 3 hydrogens. Those are all identical. So you have to have different things attached. When it comes to multiple stereogenic centers, we want to be able to identify those pretty easily. Larger molecules can have 2, 3, dozens, hundreds, okay? And just a few examples, and some of these are kind of interesting compounds. So this one is called Darvon. It is an opiate, so it's a relatively mild opiate used for treating pain. This next one, all right, this next one, ephedra, or ephedrine rather, ephedrine, it's a stimulant related to things like methamphetamine and also pseudoephedrine, which is Sudafed. They're structurally related compounds, but this one is a stimulant, and it can be used to make some illicit drugs. So this one is on a registered list. This one is fructose. We'll find that all sugars are essentially are going to have lots of stereogenic centers in them. This one happens to have 3. Let's see, that's fructose. Glucose, I believe, has either 4 or 5 of them. I'd have to look at it, but lots of stereogenic centers in them. That's fructose. And then here, this one is called beta endorphin, and it is a powerful pain reliever that is released from your pituitary gland. And so whenever you take something that is an opiate, it does release these beta endorphins. If you look, I think I counted them correctly, and I think there's 33 different stereogenic centers in this molecule. So, and that is, as far as polypeptides go, that one is relatively small. If you get an enzyme, it may have hundreds or even thousands of stereogenic centers. The point is, if just one of those stereogenic centers is in the other configuration, it is a different molecule, and it may work with a different level of effectiveness. It may be more effective, it may be less effective, or it may not work at all. So, or it could be deadly poisonous. So it's just kind of a curious thing. These stereogenic centers make a big difference. So we've talked about enantiomers, and we know that enantiomers are stereoisomers that are non-superimposable mirror images of each other. They always come in pairs, so you don't have 3 enantiomers of each other. You have 2 enantiomers of each other. They're always in pairs. Okay. Here are a couple of examples. This one is alanine. Alanine has 1 stereogenic center. Here is its mirror image. If you attempt to superimpose, you'll find that this carbon does not superimpose. So that one is, these are enantiomers of each other. Here we've got 3-bromohexane, and with 3-bromohexane, we've got 1 stereogenic center at carbon number 3. And those are mirror images of each other and non-superimposable. When it comes to drawing enantiomers, in the previous section, we drew enantiomers. We drew enantiomers by drawing the mirror image, and that's always one way that you can do it. If you have one stereogenic center, you can do this, and it's relatively easy. If you have one stereogenic center, there's another way you can do it, and that is simply to switch two of the groups on that stereogenic center. So, for example, this is 2-butanol, and in 2-butanol, you'll see that the OH attached to this carbon, here the OH is a wedge, and there it is a dash. Well, if you switch the hydrogen and the OH, you will get the enantiomer. These don't look like mirror images, but if you took this molecule and rotated it around, it would be the mirror image. So these are enantiomers of each other. So again, if you just have one stereogenic center and you switch the configuration at that one stereogenic center for two of the atoms, you will get the enantiomer. Pretty cool. All right, recognizing stereogenic centers in cyclic compounds. So to find the stereogenic center on a ring, always draw the rings as flat polygons. Okay, so here is an example. This is methyl cyclopentane. And then look for tetrahedral carbons that are bonded to 4 different groups. Now this one ends up not having a stereogenic center, but it's good to recognize that certain cases are not going to have stereogenic centers. So here we've got a carbon that has a methyl. There's an implied hydrogen on it, and then there's CH2, CH2. Since those are identical, you have to look at the next carbon. And here we have another CH2 and CH2. And then we've got a bond between those two carbons. So that means that this attachment to this carbon is the same as this attachment. So 2 identical groups, and then we meet at that ring. And so that means that is not a stereogenic center. Sometimes you have to go a couple of atoms before you get to a point of differentiation, but you go as far as you need until you get all the way to the other side of the ring. And here is a case. This one is 3-methylcyclohexene, and so there is the alkene. And so if we look, this carbon has a methyl, a hydrogen, a CH2, and a CH that's part of that double bond. That's 4 different things. That is a stereogenic center. All right, stereogenic centers in rings. All right, so in that 3-methylcyclohexene that we just looked at, the CH3 and the hydrogen substituents are drawn above and below the plane of the ring with wedges and dashes. So here is the way we could draw it, where we have the mirror images. All right, so this is a mirror image of that. Here's a ball and stick model that are mirror images. But we can also omit the hydrogen atom, because hydrogen atoms on skeletal structures are implied if you do not draw them. And so as long as we put this one as a wedge, it's implied to have that dashed hydrogen there. So it turns out that here, there is an implied hydrogen on that carbon. And we do want to pay close attention to that when we're doing these problems. So let's look at number 52 on our in-class assignment. All right, so here is number 52. So locate the stereogenic centers. I'm actually going to get my red pen here. And we want to look for carbons that are sp3 hybridized. That means everything in the ring, we can throw that out because those are sp2 hybridized. I'm going to scoot my camera back just a smidge. Get a different angle there. So this is an sp3 hybridized carbon. It's got NH2, a hydrogen that's implied, the sphenyl ring, and the carbonyl. So this is a stereogenic center. I'm just going to put a little circle around it to indicate that it is a stereogenic center. This particular carbon is sp3 hybridized. It has a nitrogen, a hydrogen that is implied, a carbon that is got a sulfur on it, and a carbon that's part of a carbonyl. So that is also a stereogenic center, as is this one. That is also a stereogenic center. And if we work our way around, this one isn't because we've got the two methyls. This one isn't because it's a carbonyl. And then this one is because it's got COOH, nitrogen, hydrogen, and then a carbon with two carbons on it. So that's 4 different things there. So we've got 4 different stereogenic centers. So amoxicillin, that is chemically related to penicillin. We'll find that all of these type of antibiotics have this beta-lactam, which is that 4-membered ring with the carbonyl and the nitrogen. And then they really, when they make different versions of penicillin and these amoxicillin kinds of drugs, they just go through and put different substituents on here, and that helps the molecules get to different parts of the body. But it's this part that is acting as the antibiotic. So kind of cool. All right, here we've got another one. This one is used in birth control pills. It's one of the drugs that is in most birth control pills. And we want to look for stereogenic centers. Again, we can rule out anything that's CH2 or these carbons that are sp2 hybridized. But we will find that this one is a stereogenic center, as is this one, this one, this one, this one, and that one. All right, we can rule out these ones that are the CH2 and of course the CH3, and then that one's sp hybridized, so it can't be. But all of these bridgehead carbons end up being stereogenic centers. If you change one of the configurations on one of these, it's a different chemical and will have much different properties in your body. So kind of interesting. All right, this one is heroin. I keep showing you guys like illicit drugs and things, but I mean, here, these are legitimate drugs, so, you know, I might as well show you an illicit one. This is heroin, which is chemically related to morphine. Morphine is just like this, except for it has OH here instead of these carbonyls, the CH or the CO, CH3. So that one is heroin, very addictive. Obviously not something that you want to accidentally take. All right. And so if we look, we've got this interesting bridge that's coming up at us and then back down and goes to that nitrogen. And so we can rule out the ones that are in the benzene ring here or the aromatic ring, but we'll find that this one is a stereogenic center. Let's see, this one, and that one. So those, all 5 of those are stereogenic centers. And I believe we have found them all because we've got sp2 here, and then these are sp3, but they have CH2. So yeah, I think we've got them all. So that one, that is that. Again, if these were different configurations, it would be a different drug. It would behave differently in your body. It might still be an opiate, but it would definitely behave differently. Okay, so now that we have looked at identifying the stereogenic centers, we want to be able to assign what the stereochemistry is. Oh, and before we do that, I just want to point out a few other drugs that are kind of big deal, or a few other biologically active chemicals. So there was a drug that was that's still in use, but it was used. It was developed, I believe, in the 40s or 50s, and then started being used, and it was very effective at treating nausea. And when they were analyzing this, they found very few side effects in the people that they tested it on. However, they didn't test it on people who might be pregnant, but then they gave it to people who might be pregnant, and or gave it to people who definitely were pregnant, who had morning sickness. And it turns out that this particular isomer is effective at relieving nausea, but the enantiomer of it is a fairly potent teratogen and causes really horrible birth defects. And so, so to the extent that any of this isomer was in with the original isomer, that caused potential for horrible birth defects. There were tens of thousands of pregnancies that were either lost or resulted in very horrible birth defects. So now, before you say, oh, well, couldn't they just isolate this one? It turns out that if you take this particular isomer only, some of it in your body gets converted into the other one. And so really, this is just contraindicated for anybody who is pregnant or who might be pregnant. But they have found that it is effective in helping people who are doing chemotherapy on a cancer chemotherapy regimen. And in certain other cases, I believe it's been used with HIV as well. But it is effective for what it does. It's just very high risk. So this is one of those, I believe it is one that has a black box warning on it. All right, I just paused the video or paused the recording and I looked it up, and yes, it does have a black box warning on it, which means it's like very prominently labeled on the box, and so they make sure that people who are taking it are not pregnant or at risk of becoming pregnant. So, in any case, one positive about this drug is that it changed the way that the FDA approved drugs. So it did have a positive benefit in that respect. All right, well, next we want to look at a few other biologically active chiral compounds. And so here we've got sucrose known as table sugar. And of course, it is delicious. It's sweet. We crave the stuff. We use it all the time. We probably get too much of it here in the United States, but oh my goodness, it tastes good. Well, when it's used the right way. And you'll notice here that it's got 9 stereogenic centers in it. And if one of those stereogenic centers were different, it would be a different molecule and would probably have a different level of sweetness, and would be processed by the body differently as well. That said, there's fructose, glucose, and then sucrose is the combination of those. And your body is pretty effective at converting all of those into glucose. All right, the drug over here on the right, you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different stereogenic centers in this one. And this is called Taxol, and it is an effective anti-cancer drug at slowing down cancers. And it has been found over the last almost 30 years to extend the life of some 800,000 plus cancer patients, and that's just in the United States. In other countries, it has been used as well. And so it is, like I said, very effective. It is pretty expensive, even though it is not on patent anymore. It's still pretty expensive because it's a very complicated molecule. All right, so now we want to look at labeling stereogenic centers as either R or S. So we have a method of saying which enantiomer is which, but it takes a systematic way of doing it. And so to do that, we're first going to look at, R and S are the two different ways we can designate a particular stereogenic center. But before we do that, we need to learn how to assign priorities to the different groups that are attached to a stereogenic center. So find your stereogenic center that has 4 different things attached to it. Here, I've got a very simple one. It's got 4 different things attached to it. And then we're going to use what's called the CIP priority system. So this is the Kahn-Ingold-Prelog. Those are the people who came up with this system, the CIP system. And when we look at this, we've got 4 different things attached. And the rule is assign the highest priority to the atom with the highest atomic number. And the lowest, and the highest priority is going to get the number 1, and the lowest priority is going to get the number 4. And you just work your way down. Since these are 4 different atoms, this is pretty easy. I'm going to go over to my periodic table that I have here. Our 4 different elements that are attached, and we go back. So our 4 different elements that are attached here are bromine, fluorine, chlorine, and hydrogen. So we'll come back over here. There's bromine, there's chlorine, there's fluorine, and hydrogen. So bromine is the biggest with an atomic number 35. Chlorine's next, then fluorine, and then hydrogen. So when we come back over here, highest priority is bromine at atomic number 35, chlorine at atomic number 17, fluorine at atomic number 9, and then our lowest priority 4 is hydrogen at atomic number of 1. All right, so that's our first rule. Now, sometimes we'll have the same atom that's attached, but it is a different group. So if we want to assign the priorities for things that are the same atom, so if we have 2 atoms that are the same, assign the priority on the based on the atomic numbers of the atoms bonded to these atoms. So let's look at an example. This is 2-butanol. And clearly, there are 4 groups here. We've got oxygen, hydrogen, carbon, and another carbon. Well, oxygen is the biggest. We'll come back over here. Oxygen is the biggest at an atomic number of 8. Hydrogen is the smallest at an atomic number of 1. And then we have 2 that are carbon at an atomic number of 6. So 1 is going to be the oxygen, and 4 is going to be the hydrogen. But then these we have to assign by going to the next atom. So this one's either 2 or 3, and this one is either 2 or 3. Whichever one the other one was, this one is the different one. Okay. So when we look at what is attached to this particular carbon, the CH3 carbon, well, there are 3 hydrogens. So we have hydrogen, hydrogen, hydrogen. This one is attached to another carbon and then 2 hydrogens. So our CH2-CH3 group, we've got a carbon and 2 hydrogens that are attached to this particular carbon. Well, we're looking for the first point of differentiation. Since they're both carbon, we'll look for, we put them in order of decreasing atomic number. And since the carbon here is bigger than hydrogen, carbon has an atomic number 6, hydrogen's atomic number of 1. We just need 1 point of differentiation to make the call, and that means this one has a higher priority. All right, so that one has a higher priority at carbon. We're going to call that one 2. So this will be 1 and 4, but this will be 2, and this will be 3. All right, so rule 1, atomic number. Rule 2, if you have a tie, then go to the next atoms and see your first point of differentiation. For rule 3, if we've got isotopes. Now, we don't do a lot of isotopes, but occasionally there are isotope studies when you are looking at molecules. You may want to label a particular atom with an isotope. There's all kinds of cool tricks you can do with that. If you've got 2 isotopes bonded to a stereogenic center, assign the priority based on the order of decreasing atomic mass. So here, we've got 2 hydrogens, but one of those hydrogens is deuterium. And deuterium is just hydrogen. So there's 1, and that's 2. These are 3 and 4. Hydrogen is just 1 proton. There are no neutrons in regular hydrogen. But deuterium, there's 1 proton and 1 neutron, so it has a mass number of 2. So since 2 is bigger than 1, this one will have higher priority, so that'll be 3, and the hydrogen will be atom 4, or priority 4. All right, so that's rule 3. Rule 4, all right, to assign the priority to an atom that is part of a multiple bond. Treat a multiply bonded atom as an equivalent number of singly bonded atoms. So if this is one of the substituents on a tetrahedral, now it couldn't be a tetrahedral itself because it's sp2 hybridized, but if it's attached to a tetrahedral, we treat this carbon as if it is bonded to 2 oxygens. So it's got a bond going to oxygen and another bond going to oxygen. If you need to go another step, so it's got a bond to oxygen, another bond to oxygen, and then a bond going to hydrogen. So oxygen, oxygen, hydrogen. If you need to go to another step, then you would count the bond that's going back to this carbon. So again, that's just for tiebreaker purposes. All right, here are a couple of other ones. So on this one, we've got a carbon. This carbon has 2 bonds going to carbon and 1 bond going to hydrogen. So bond to carbon, a bond to carbon, a bond to hydrogen. And one of those carbons we're going to designate that has a bond going back to your original carbon. So again, that's for tiebreaker purposes if you get stuck on one. All right, here with the triple bond, this is equivalent to 3 single bonds going out to carbon. So carbon, carbon, carbon. And then one of those carbons is going to have 2 bonds going back to our original carbon. So we'll count that as 2 more carbons. But again, that's only a big deal if you need a tiebreaker. Okay, well, let's look at this particular, these particular examples, and then we're going to look at number 43 on the in-class assignment, and 43 is pretty easy. So if we're assigning priorities to this carbon, so here we've got the 4 atoms are bromine, hydrogen, chlorine, and carbon. Well, bromine has the highest atomic number. All right, chlorine is next, and then carbon, and then hydrogen. All right, so bromine, chlorine, carbon, and then hydrogen. Now, sometimes people look at this one and they think, oh, well, we've got an iodine. Isn't the iodine bigger than the bromine? Well, iodine is bigger than bromine. However, we count the first carbon first, and we only look at attached atoms to that element if we have a tie. All right. The next one, we're going to have a bunch of ties because we got a whole bunch of carbons. So this would be 1, 2, 3, 4 would be our priorities. So now looking at this one, we've got 4 carbons attached. So we need to look at what else is attached. All right. The isopropyl group gets the highest priority because this carbon has 2 bonds going to carbon and 1 to hydrogen. So this is a carbon with 2 carbons and a hydrogen. These are carbons with 1 carbon and 2 hydrogens, so they're higher priority. And then this methyl has 3 hydrogens attached, so it's going to end up being the lowest priority. Now, to do the tiebreaker to this one, you look at the next carbon. Don't go all the way to the end and say, oh, this one's longer, so it's got to be the higher one. You've got to look at what else is attached. So CH2, we look at what's attached, hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon. So then we come here, we've got a CH2, another CH2, so we need to go to the next atom. CH3, CH2 with a carbon attached. So this one, because this is our first point of differentiation, this is going to have the higher priority than this one. All right, and then on this one, we've got hydrogen and oxygen. So oxygen's bigger than the 2 carbons, so it has the highest priority. The hydrogen has the lowest priority. And then we've got a CH2O, so it's a carbon with an oxygen, hydrogen, hydrogen. And then this carbon has 2 bonds going to oxygen here and an additional bond going to oxygen. So this carbon has 3 bonds going to oxygen. It will have higher priority than this carbon, which only has 1 oxygen going to that carbon, or 1 bond going to oxygen from that carbon. All right, let's look at 43 on the in-class assignment. And 43 is pretty easy. And we're just assigning which one has the higher priority here. So we have OH versus NH2. Well, since oxygen's bigger than nitrogen, the OH will have higher priority than the NH2. All right, carbon and carbon. So those are the same atom. We need to look at the atoms that are attached. So this carbon has a deuterium, deuterium, deuterium. This one has hydrogen, hydrogen, hydrogen. So the first point of differentiation is that the first deuterium and hydrogen, and so this one will have a higher priority than the CH3. All right, here we've got isopropyl group and a, let's see, CH2OH group. All right, and so we look, this carbon, if we look at the atoms that are attached, this carbon has a carbon, and a hydrogen attached, whereas this carbon has an oxygen, a hydrogen, and a hydrogen attached to it. Well, we look for our first point of differentiation, carbon versus oxygen. Since oxygen's bigger, this is going to have our higher priority. All right, here we'll look at this one. This carbon's got chlorine, hydrogen, hydrogen. This carbon has carbon, hydrogen, hydrogen. So chlorine is bigger than carbon. This has a higher priority. We don't get all the way down to that bromine because we had a point of differentiation on the very first carbon. So that makes that one have the higher priority. All right, so CHO, just as a reminder, let's see, CHO is equal to, when we've got a carbon, double bond, oxygen, hydrogen, so that's an aldehyde. COOH, that's carboxylic acid, so COOH is equal to carbon OH. So if we look, this carbon has 2 bonds going to oxygen, 1 going to hydrogen. So we'd say oxygen, oxygen, hydrogen. And this one has oxygen, oxygen, oxygen. So our first point of differentiation is that we've got 3 oxygens instead of 2. So this will have our highest priority. All right, and then finally this one. This one's kind of interesting because these are actually isomeric of each other. So we have CH2NH2, and this one is NHCH3. If we look, this is carbon, this is nitrogen. Well, that's our first point of differentiation. Nitrogen is a larger atomic number than carbon, so nitrogen wins, so that's the highest one. All right, so that is number 43. So now we want to figure out how to assign R and S values. And so to do that, we're going to look at this example, which is, this is 2-butanol, which is actually butan-2-ol. We'll name alcohols a little bit later. All right, so the very first thing that we want to do is assign the priorities of each group in the stereogenic center. And so our priorities here are that the oxygen has the highest priority. We've got a hydrogen that has the lowest priority, a CH3, and a CH2CH3. So since this carbon has another carbon attached, it will have the second priority. So ethyl will be second, methyl will be third, and then hydrogen will have the fourth priority. So oxygen, carbon, carbon, and hydrogen. And again, we got, this is carbon, hydrogen, hydrogen. This one's hydrogen, hydrogen, hydrogen. So this one has the higher priority. All right, step 2, once we know the priorities, we want to label them, and we want to orient the molecule so that the lowest priority, priority 4, is in the back. And then usually once I've put that priority 4 in the back, once I put it in the back, then I don't label it anymore. So those are our 4 things, and then we're going to label this one. So oxygen is 1, and then here that one's 2, and this is 3. And again, we're not going to label group, the 4th priority group. It's just in the back. We're going to ignore it. Poor hydrogen's always getting ignored like this. All right, next on this one, we'll see that we've got, there is 1, this one's 2, and this one's 3. Once you have this drawn correctly, and you've got that smallest atomic number in the back, then we're ready to determine whether it is R or S. So we're going to trace a circle from priority group 1 to 2 to 3. So on this one, we're going to go from 1 to 2. We'll do a little loop there. So from 1 to 2, and then we'll do an arrow from 2 to 3, and then from 3 back to 1. All right. And then here on this one, we'll go from 1 to 2. You'll see it goes the other way. And then from 2 to 3, and then 3 back to 1. Well, if tracing the circle goes in the clockwise direction, as this one does, so that's clockwise, then the stereogenic center is designated as the R configuration. If tracing the circle goes in the counterclockwise direction, as it does here, so here it's going in the reverse direction as a clock, then the stereogenic center is designated as S. And it is perfectly reasonable if you have trouble remembering which way is clockwise and which way is counterclockwise. It is perfectly reasonable to have a just regular watch on, right? Regular watch like here. I've got this one, and that way you can remind yourself which way is clockwise and which way is counterclockwise. All right. Hopefully you won't have that trouble. All right. So this one is R and this one is S. So that one is R and that one is S. All right. And there are some tricks for orienting the molecule. We saw this in the previous section, or one of the previous sections that we did. If the lowest priority group is not facing towards the back, we can rotate the molecules 120 degrees around any stationary bond axis. And we can also flip the molecule by 180 degrees if that happens to be convenient. So here our lowest priority 4 is not in the back. If we keep the 2 where it is and keep this carbon where it is, we can rotate about that, and then this 4 will go over here to the back, the 1 will come over here to the left, and the 3 will come out to the front. So it will rotate 120 degrees about this bond. If you have the 4 coming forward and you want to make it so that it is going back, so another trick is that you can just take that molecule and flip it 180 degrees. And let's see, to illustrate this, I'm going to just put a molecule in here, and I'm going to pick one of our, so this one we had earlier. So, all right, so let's say that this is hydrogen and it's in the front. So this red one, kind of get that all lined up here. This red one is this atom number 2 there. Atom number 3 is the yellow one that's right there. 4 is the hydrogen that's coming out front, and then 1 is this green one that is in the back. So we're going to rotate about this carbon, or whatever this red-black bond is, and when we do, all right, now I'm the red, black, and green are in the plane. So we have 2, there's the black one, and there's the green one. And then you'll see that the yellow one that was here, it was over here, came here, and then the white one, which is the hydrogen, went to the back. Okay, so that's one way of looking at it. So again, it was like this. All right, and then we just rotated it to get it like that. And so you can rotate about any of the 4 bonds, and it's okay to practice those if you need a little help practicing them. The other trick is, let's go back to, I'm just going to pick the same one here. So let's say we have yellow, black, red, and so that's going to be 3 carbon and then 2. And then we have our, here, let's get it this way. So here we have black, red, black, yellow. So that's 3 carbon and then 2. And we have a hydrogen that is coming towards you, and then the highest priority green is going back away from you. So one trick that we can do is just to take it and flip it over 180 degrees. And when we do, these 2 switch positions and these 2 switch positions. So 2 and 3 switch positions, and 1 and 4 switch positions. So again, so you'll notice the red and yellow switch positions when I turn it around, and then the white and green switch positions when I turn it around. All right, so that is one of the tricks that we can do. So let's look at number 45, and we want to designate all of these as R or S. So designate them all as R or S. And let's move that in just a smidge. Now, some of these we may need to do a rotation in order to determine whether it is R or S. So if we look, our highest priority for this stereogenic center is iodine. So that is 1. And then our hydrogen is 4, and the hydrogen happens to already be in the back, so we're good there. And then we've got CH2, CH3, and then here we've got CH3. Since this carbon has a carbon attached and this one doesn't, this one will have priority 2, and this will have priority 3. So since the hydrogen is in the back, we can go ahead and look at this one, 1 to 2, 2 to 3, and then 3 back to 1. You'll see that that is counterclockwise, so this is the S isomer, and that's how that works. All right, so let's look at this particular carbon. On this carbon, we've got hydrogen, CH3, NH2, and CH2, CH3. Well, our highest priority is clearly the nitrogen, and our lowest priority is the hydrogen that's coming out towards us. We've got another CH3 and then CH2, so this one is going to be 2, and this one is going to be 3. Now, I'm going to redraw this, and there's a couple of different ways that we can redraw it. We can either rotate about like the carbon-nitrogen bond, or we could flip it. And if we flip it, then these two will change position, and then 3 and 4 will change position. So let's go ahead and redraw it in that flipping it way. And again, just kind of imagine that I'm doing an axis that goes right through that carbon. The 3 and 4 will switch position, and 1 and 2 will switch position. All right, so carbon, CH2, CH3, and then CH3. So you'll see that 1 and 2 switch positions. And then now our CH3 is coming forward, and the hydrogen is going back. So now let's label our priorities. Oh, this is NH2. I goofed that up. All right, so let's just fix that real quick. And we'll call that NH2. Because I was looking at that and we had 2 of the same thing. So 1 and 2 switch position, and then 3 and 4 switch position. All right, so now let's label the priorities. Nitrogen versus carbon versus carbon. Nitrogen has the highest priority. The CH2CH3 has the second priority. Our third priority is this methyl. And then the hydrogen's in the back, it's 4. We're not going to label it. And now we are going to draw our arrow from 1 to 2. Oh, I was going to draw that in red here. So from 1 to 2, from 2 to 3, and then from 3 to 1. And you'll see that's counterclockwise. So this is also S. Don't worry, we're going to get an R in here somewhere. All right. So on this one, you'll notice that our lowest priority, so we've got carbon, tritium, deuterium, and hydrogen. So hydrogen has 3 isotopes. Hydrogen just has 1 proton. Deuterium has 1 proton and 1 neutron. And tritium has 1 proton and 2 neutrons. So tritium has a higher priority than deuterium. And then hydrogen is going to be our lowest priority. The carbon will be our highest priority because it is it has a higher atomic number. So that's 1, 2, 3, and 4. We want to get that 4 to the back. So I'm going to rotate about this carbon-tritium bond. Okay. And the hydrogen, we're going to rotate it to the back. So hydrogen, and I was saying hydrogen, and then I went ahead and wrote down CH3. All right, let's try that again. So hydrogen is going to the back. So we rotate there. The deuterium is going to get flipped up here to the top. And then our CH3 will be in the front now. So that hydrogen is in the back. Since it's going away from us, we'll now label this. Our carbon has the highest priority. Tritium is second. Deuterium is third. And that is the deuterium there. And the hydrogen is fourth, but we're not going to label it. When we start the arrow, so it goes from 1 to 2, from 2 to 3, and from 3 back to 1. You'll see that's clockwise, and so this is the R configuration. So this is the R configuration. All right. So now let's look at this one. We've got 4 different things attached to this carbon. We've got a carbon, a bromine, a chlorine, and a hydrogen. Our highest priority of the carbon, bromine, chlorine, and hydrogen is going to be the bromine. We can ignore the iodine because it's on a carbon. So bromine has the highest priority. Then chlorine is second. Carbon is third. And then our, let's see, what is it? Our hydrogen is fourth. I think the easiest way to do this one is to rotate about the carbon-chlorine bond. So we're going to draw that carbon-chlorine bond. So chlorine, carbon. And we're going to rotate it. We're going to rotate it so the hydrogen goes to the back, the bromine comes up to the front, and then the CH2I comes over to the right. So we'll have CH2I there. Our hydrogen went to the back. And our wedge that comes out to the front here is going to be bromine. Now when we label the priorities, bromine is 1, chlorine is 2, carbon is 3, hydrogen is 4. We're not going to label it. We'll go from 1 to 2, from 2 to 3, and from 3 back to 1. Well, that is clockwise, so that is the R isomer. So that is the R isomer. Okay, this one has 2 stereogenic centers. So this is all kinds of fun. You can, if you want, redraw it, or you can just kind of figure it out as we go along. Let's see here. So we've got, let's look at this particular carbon. The 4 things that are attached are OH, hydrogen, CH3, and then a carbon that has a sulfur, a carbon, and a carbon attached. So our highest priority here is going to be the oxygen, so that's 1. Lowest priority will be the hydrogen, which is 2. That's convenient because that puts the hydrogen in the back, which means we don't need to rotate this one. So it puts that hydrogen in the back. Now, let's see. So 1, there's 4, and then this one has our second priority, and this one will have our third priority. All right, so there's 1, 2, 3. So 1 to 2, 2 to 3, and 3 back to 1. That's counterclockwise, and so that is S. That is S. All right, and then for this one, here it would be helpful if I had a different color. We'll try green. We'll see how that works. All right, so here this carbon has 4 things attached. It's got a sulfur, a methyl, a carbon with an oxygen, and then a carbon with 2 carbons on it. Our highest priority is going to be the sulfur. The carbon with an oxygen on it will be second, and then this this carbon that has 2 carbons on it, that'll be third, and our fourth is actually already pointing back, so that's kind of convenient. We'll go 1 to 2. 2 to 3, and 3 back to 1. You'll see that's clockwise, and so that is R. Now, if you get confused, this is where the video is really helpful. You can rewind and go back and hopefully follow along. If you have questions, make sure you contact me during my office hours, and we can go over that. All right, so we have S and R on that one. So let's look at this one. Here we've got a carbon, and that carbon has a carbon, a carbon, a carbon, and an oxygen. Well, oxygen has the highest priority, so that's 1. And then this carbon has 3 bonds going to oxygen. This carbon has a bond going to nitrogen, 1 to hydrogen, 1 to carbon, and then this carbon has 1 bond or 3 bonds going to hydrogen. So our lowest priority is that methyl that's in the back. Our next after oxygen is this one, and then this is 3. Since our lowest priority is in the back, put a little 4 there. Our lowest priority is in the back. We can go ahead and do the arrow on this one. So 1 to 2, 2 to 3, and 3 back to 1. That's clockwise, so this is the R configuration for that carbon. If we look at this other carbon, this one isn't oriented correctly because the hydrogen, which is our lowest priority, is coming forward. So I'm going to rotate about this carbon-carbon bond, take this hydrogen, move it to the back, the NH2 will come down to the bottom, and the CH3 will come out to the front. And so we've got carbon, carbon. I'm just going to redraw all of these. So COOH, and then CH3 is going back. Our wedge here is OH. All right, so I recreated that one. And now we're going to move, we're going to move that NH2 down here. All right, when we did that, our hydrogen went back, and our CH3 came up to the front. So this one would go to the back, this one came to the bottom, and then the CH3 came up to the front. And now we can look at this, and we've got, let's see. So we've got nitrogen, CH3, and a carbon with an oxygen. So the nitrogen has the highest priority. This carbon with an oxygen is second. The carbon with 3 hydrogens is third. And our fourth is that hydrogen. It's going back, so we can ignore it. And then we go 1 to 2, 2 to 3, and 3 to 1. That is clockwise, so that is R. So this one is also the R isomer. So just in case this got a little too messy for you guys to stay clear, here we had RR. Okay, I'm going to redraw this one on the back. Just give me a second. All right, sorry about the little jump edit there. So I've redrawn this molecule exactly as it was drawn to begin with, except, you know, it's written instead of typed, but you get the idea. So I've redrawn that molecule. We already know that this one is R. We've already designated that one as R. But we're going to do the configuration on this carbon, except I'm not going to rotate it around. I'm going to leave that hydrogen where it is, where the hydrogen is coming forward. And you can do a little trick here with this. So our highest priority on this carbon is going to be the nitrogen. So that's 1. This carbon over here is priority 2. And then the CH3 is priority 3. So now when we do the arrows, we got arrows going from 1 to 2, from 2 to 3, and from 3 back to 1. You can clearly see that that is counterclockwise. However, we're looking at it from the back. And if you look at it from the back, that means that if you were to turn it around and look at it from moving that hydrogen to the back, then it would be clockwise. So if your smallest group, your priority 4 group, is coming forward, then just do the opposite. So since this one's counterclockwise, this one is R. And that gives us our same configuration that we had for this. Again, you can practice that. If you get stuck on it, feel free to ask. All right, now we've got another stereogenic center here. On this stereogenic center, this one's not a stereogenic center because it has 2 methyls on it. But on this stereogenic center, we've got hydrogen, which is going away from us conveniently. I'm not going to draw it in there, but we know it's there. We've got a methyl, a CH2 with a carbon, and then a carbon that has 3 carbons attached. Our highest priority is going to be that carbon. CH2 is going to be second, and our CH3 is going to be our third priority. If we look, we'll get 1 to 2, 2 to 3, and 3 back to 1. That's counterclockwise, and that means this is the S configuration. So this one is S. Should make that a little bigger there, right? There's an S that is right there. Okay, finally, let's do this one. We've got chlorine. We're going to look at this one first because the hydrogen's going back on this. Chlorine has the highest priority, and then this carbon has second priority because it's got a chlorine attached, and this one doesn't have any chlorine. It has a carbon and 2 hydrogens, so it's third. So 1 to 2, 2 to 3, and 3 back to 1. That's counterclockwise, and so this is going to be S. Now for convenience, I'm going to redraw this so we can look at the other one. So there's chlorine, and then we have a wedge with chlorine. So let's look at this one. On this particular carbon, which is that carbon 2 that was right there. So on this particular carbon, we've got a chlorine, which has the highest priority. We've got a carbon with a chlorine, which is 2. And this CH2 carbon with 1 carbon and 2 hydrogens, that's priority 3. Priority 4 is the hydrogen that's implied that is coming towards us. And if we look, this is 1 to 2, 2 to 3, and 3 to 1. That's clockwise. Clockwise normally would be R. However, because the hydrogen's coming forward, this one is S. So that means that these two carbons have the same priority. I'm going to show you one little trick before we end this video. All right, so there is our original compound again. So it's the trans 1,2-dichloro trans 1,2-dichlorocyclohexane. Okay, sorry again for the weird jump cut, but I've rebuilt this molecule. This is a cyclohexane, and of course cyclohexane would have a chair structure, but you can see I have forced this to be in an all eclipsed conformation. I've put angle strain in there because the angle's at 120 instead of 109, but I did this on purpose so it would look more like this particular structure. And so you'll see that here I've got the chlorine that is going back on this carbon and the chlorine that's coming forward on this carbon. And I want you to see this little trick, right? We saw that this was S and S. And so we know that this one here is S. All right, we know that is S, and we know that this one is also S, so they have the same configuration. Well, if we take this molecule and rotate it around like this, we get the same molecule. So you'll see that the one that was in the front got into the back, and the one that was in the back came up to the front because, again, we rotated about this axis. And when we do that, we just keep reproducing the same thing, which means that's a trick that you can do is if you've got a trans like this and it's 1, 2, you can do a flip, and you'll see that it's exactly the same configuration. And that's one of the little tricks I like to do. All right, well, we're going to end the video there, and we'll pick up in the next section talking about diastereomers.